This is the part 2 of board exam revision. This video involves the theory part mostly, not involving with the deep reactions and mechanisms like we are studying for JEE or NEET, JEE Advanced. So let's get started with this chapter, amines. We already finished electrochemistry, biomolecule solutions, and aldehydes chapter. If you didn't watch that video, please do check out. Let's start with the amines. Amines are the derivatives of ammonia obtained from replacing one or more hydrogen atoms from the ammonia structure by replacing it with alkyl or aryl groups. Right? It is an sp2 hybridized pyramidal geometry like we have for ammonia. The fourth orbital has a lone pair and the bond angle is 109.5. It's for a tetrahedral shape. 108 in trimethylamine, which means all three hydrogen is replaced by the alkyl or aryl groups. Alkyl groups basically over here. Okay, why that is happening? Because of lone pair repulsion. Okay, mostly in board examination you can expect the questions like why that is happening, why this is happening. That's that kind of question. That's why this whole revision is concentrating more on theory part rather than the reactions, because as my viewers, you already know those reactions very well. Okay, then classifications of ammonia, primary, secondary and tertiary, replacing one another hydrogen. So you will get with these kind of classifications, right? Then nomenclature. This nomenclature is a bit different from other functional group nomenclatures. As you can see, primary, just we'll mention it as amines. Secondary and tertiary amines, we'll use N for locating the position and mentioning N is attached with which group. Okay, which group is attached with the N. Similarly, it applies for tertiary as well. See the common name and IUPAC name. This is aniline, orthotoluidine, which is 2-methyl-aniline, and N, N dimethyl-aniline. So which means aniline is there and two methyl groups are also present over there. Okay. Then moving on to the preparation of amines. As a regular preparation which can be prepared by the reductions from the nitro group using hydrogen palladium or tin HCl, we can also use FeHCl. FeHCl is more preferred than the tin HCl. Tin HCl, because FeHCl formed gets hydrolyzed, release HCl that can be used again for the reaction. So that's why we are using Fe plus HCl combo. Okay, then ammonolysis of alkyl halides. That is also a preparation method to prepare amines, where we'll get primary, secondary, tertiary and quaternary amines also. So each one of the time you are adding more and more Rx group to it, it will replace the hydrogen with the R group. Okay, so that is what. Otherwise, it's also called as half-mode ammonolysis. The disadvantage of this method is that it gives a mixture of amines. Right, primary, secondary, tertiary, mixture of amines. So yield will be less for the particular amine. The next one is reduction of nitriles. CN group can get reduced to form CH2NH2. Okay, so starting amine will have a less number of carbons in the name than the ending. For example, if I'm taking methyl cyanide, which will be producing ethylamine. Okay, so that is the difference you would see here. Then we have reduction of amides to amines, that is RCONH2 with lithium aluminum hydride gives RCH2NH2. From cyanides also you can prepare amines, from amides also you can prepare amines. And then another interesting method to prepare amines, that is Gabriel thallamide synthesis. This method is particularly for primary aliphatic amines only. Primary aliphatic amines only. We'll take phthalic anhydride, right? Add base KOH, which will give you potassium thallamide salt. After that, we'll add RX to get that particular R-related amine. Okay, this is for primary aliphatic amines only. It can't use to prepare. We can't use it for aromatic primary amines. Then the next important method, important named reaction, that is Huffman bromamide degradation. So many times we have seen this in papers, right? Br2 with NaOH, Br2 with KOH. Basically, Br2 with a base, strong base. What is the reagent? What is the reactant used over here? That is amide. Amide to amine. One carbon less you will get. Okay. In the first method, I already, you may ask, ma'am, already I have a method to reduce amide to produce amine. Why I have to follow this method? In this method, you see one carbon less is produced. For example, if you are taking CH3CONH2, you will get CH3NH2 only through this method. using Br2KOH method, Huffman bromamide degradation. In the another method, you might be getting CONH2 to give CH3CH2NH2 with the reduction. Okay, that is the difference between these two methods. And this method is particularly for primary amines with 1 carbon less we will get. Okay. Then properties of amines, that is also very important in this chapter. Usually in other organic chapter they might not be asking about the properties much, but here properties are also equally important. First, this is the lower aliphatic amines will be gaseous in nature, fishy odor, that all we know. Talking about the boiling point, primary will have more boiling point, then comes secondary and then tertiary because of hydrogen bonding. Extent of hydrogen bonding happens over there. Okay. And as soon as I'm adding more and more alkyl group to it, making it bigger, what will happen? It will create more steric. So the boiling point will be less. No hydrogen bonding will be produced over there. Eventually boiling point will be less. And talking about amines and alcohols, if you are taking the similar mass also, NH bond is much weaker than the OH bond, right? Because OH is more electronegative. So the boiling point changes in the way alcohol will have more than the amines. Then solubility, lower aliphatic amines are miscible with water. Solubility decreases with chain length. And most importantly, we have to talk about the basic character. Basic character, I already told you many times. There are you have to understand few things about basic character. One is, question can be asked from giving you the Kb value. Okay, if the Kb value is higher, then the basicity is higher. If the pKb value is given, that is higher, then the basicity will be lower. Because pKb and Kb is inversely proportional to each other. Okay, then next one is, if they are giving you amines in gaseous and aqueous solution. Aqueous solution means there will be two categories. One is methylamines, another one is other than methyl. Okay, starting from ethyl. And gaseous means you can follow the normal trend for any basic, any gaseous amines. Here you see, I have aliphatic amines versus ammonia. Aliphatic amines are stronger than ammonia because of the plus I character of alkyl groups. Okay, similarly, basically what is amines? That is, what is basic? Tendency to donate the lone pair, right? So if I'm having electron withdrawing group present over there, then the tendency would be much weaker than the presence of an electron donating group. So that kind of question can also be asked. Look at the gaseous phase. The inductive effect follows tertiary, secondary and primary. So more will be the alkyl group, more will be the basicity, because alkyl group produces more electron donating ability, plus I effect. And in aqueous phase, it affected by plus I effect, solvation, steric hindrance, all. So in aqueous phase, other than methyl, we have ethyl group here. See, secondary, tertiary and comes primary. If I am having methyl group, then it will follow secondary, primary and comes tertiary. Okay. And if you are comparing aryl amines with ammonia, aryl amines are weaker than ammonia. Okay. Why that is the weaker tendency? Because in aniline, the lone pairs of nitrogen is undergoing resonance. It is undergoing conjugation. It can't donate the lone pair very easily. There is no availability much time. Right. In case of ammonia, 24/7 lone pair is there in the nitrogen. Right. But in aryl amine, it's like 9 to 5. Okay. So obviously we'll trust 24%. Right. So that is the difference. And as I told you, electron withdrawing group decreases the basic strength, electron donating group increases the basic strength. Then the reactions. So reactions with acid, it will produce salt plus water. Right. The amine salts are soluble in water and insoluble in organic compounds. And alkylation. Alkylation, amines with Rx group, one of those hydrogen will get replaced by the R group. Right. R group from the alkyl halide. Like we saw in Huffman method, Huffman ammonolysis. Then acetylation with acid chlorides or anhydrides or esters, only the primary and secondary amines will react, because in tertiary amine I don't have hydrogen in it. Okay, that will form an acetate. But acetate, CH3CO attached with the RNH group. So one of those hydrogen will be replaced by CH3CO or whatever the group you are adding over there. Then benzylation, amines with benzoyl chloride, which will form N-methyl benzenamide with HCl. Again, this will not be suitable for tertiary amines because there is no hydrogen. Then important test, that is carbylamine test. This is for primary amines only. It can be of aliphatic and aromatic, but only for primary amines. Secondary and tertiary amines will not respond. What is the reagent used over here is CHCl3, like chloroform with KOH to form methyl isocyanate or alkyl isocyanate. Not CN, it is NC. Okay, isocyanate is formed, that is recognized by the foul smell. Then the next one is reaction with nitrous acid. So the nitrous acid is prepared in situ. In situ means in the reaction vessel itself we will prepare this reagent. How? We are adding sodium nitrate and HCl. So it itself will produce nitrous acid. Okay, we are not adding nitrous acid separately. That is what the meaning of in situ. Okay, so the primary amine, if I am adding to it, aliphatic primary amine with this nitrous acid, and the temperature is maintained 0 to 5 degrees Celsius, which will produce alcohol and N2 gas and HCl. But in case of aromatic amines, it will form an highly important compound, that is diazonium salt or ArN2Cl, diazonium salt, which has a tremendous synthetic application. In case of secondary amine, it will form an yellow oil, and tertiary amine, it will give a scattered product, different products it will form. Okay, so this is an important test to recognize whether the amine is primary, aliphatic or aromatic. Okay. Then Hinsberg test, again the distinguishing test. The reagent is benzene sulfonyl chloride, C6H5SOCl. Hinsberg reagent, sometimes they will ask you this. What happens over here is, with primary amine, it forms sulfonamide, which is soluble in alkali. Okay, but in case of secondary amine, it will form again the sulfonamide, but which is insoluble in alkali, which can be given as a clue point in the question. Okay, and the tertiary amine, it will not react. That is the famous Hinsberg test for amines. Then electrophilic substitution of aniline. Aniline, which is an electron donating group, right? So electron donating group means the incoming electrophile, where that will go? It will go to R2 and para position, right? The same thing happens over here, C6H5NH2 with Br2, that will form 2,4,6 tribromoaniline, and which will not stop at mono substitution directly. If you want a mono substituted product, you have to treat it with the anhydride, acetic anhydride with pyridine. So acetanilide will form. Then we are treating it with acetic acid with Br2 to form para-bromoacetanilide. Okay, if you are adding acid or base, then it will change to 4-bromoaniline. Okay, hydrolysis to takes place, 4-bromoaniline will be formed to get mono-bromo substituted product. Why is it happening? Because the acetylation reduces the activated power of the NH2. That's why tribromo is not formed, only the monobromo is formed. Okay, that is the reason. Then nitration. So nitration, again, it will give you the mixture of ortho product, para product and meta product, because it happens in this strongly acidic medium. Aniline is protonated, so to form an anilinium ion. So that anilinium ion is a meta director. Okay, anilinium ion is a meta director, that's why meta product is also formed. So if you want para-nitroaniline only as a major product, what you have to do is, first of all, you have to protect the amine group. Okay, you have to protect the amine group. How you can protect it? Like we said earlier, you can use the bromo compound, acetyl compound. Okay, then nitrate it, then hydrolyze it to get para-nitroaniline. In sulfonation, it will form this bitter ion like this. That is sulfonilic acid to get to para-amino benzene sulfonic acid, that is sulfonilic acid, that is formed eventually. In Friedel-Crafts reactions, amine will not undergo Friedel-Crafts acylation or alkylation. Why is it so? This is an important question. So in Friedel-Crafts reaction, we will be using Lewis acid, FeCl3 or AlCl3, because that will have an empty orbital, so that will create an electrophile. Right, it will help to create an electrophile. So what will happen in amines? That empty orbital will get the electrons from the amine. Okay, NH2 lone pair. Okay, so that's why it acts as a deactivating group, so there is no substitution happens. That just a salt may be formed. There is no substitution as we expected will be formed for Friedel-Crafts reaction. Then diazonium salt. Diazonium salt I had already told you, which is from aromatic amines we prepared using diazotation method using nitrous acid. Okay, this salt is stable because it is undergoing resonance with the benzene ring. Physical properties of diazonium salt, that is colorless, crystalline, and benzene diazonium fluoroborate, that is water soluble, stable at room temperature. Here we have to see this important reactions like Sandmeyer reaction, Gattermann reaction. There is a slight difference in these reactions. In Sandmeyer, we will be using copper 1 salt as a catalyst along with HCl, along with the salt of Cu2Cl2 we will be using to get a better yield. In Gattermann reaction, we will use it separately, copper and HCl. Okay. Gattermann and Sandmeyer, comparing both the yields, Gattermann will give you the lower yield. Then if you want iodide, you can use Ki. Copper is not needed. And for fluoride, Ball-Schiemann reaction you can use by using the fluoride compound, fluoride. Then if you want phenol, then you can add simply water, like we did for primary amine, it immediately formed alcohol, right? So similarly happens over here. Then to replace with hydrogen to form a benzene, we'll use H3PO2. This is a very important question, so many times they have asked. And the replacement of NO2, you can use NaNO2 to form nitrobenzene. This diazo group can undergo coupling reaction as well. Coupling reaction is just an addition kind of thing, okay, which will lead to the formation of azo dyes. If I am adding phenol to it, it will give you orange dye. Okay, if I am using aniline to it, then it will form an yellow dye. Okay, coupling occurs the para position of the phenol or aniline because that position is activated. And the products are azo compounds which will have a N double bond N linkages with an extended conjugation. That conjugation is responsible for the colors. Then diazonium salts allow the introduction of groups that cannot be introduced by the direct substitution. Like fluoro and iodo cannot be introduced by the direct halogenation, rather than we are using HI or HBF4, right? And cyanide cannot be introduced by the nucleophilic substitution on the chlorobenzene ring. And NO2OH also, diazonium group is more selective. Other than that, these groups are introducible by this using the diazonium salt. That's why this diazonium salt is having tremendous synthetic organic application. These are the distinguishing tests. I just summarized over here, and basicity comparison that is also given. The common mistakes to avoid, just you can take a screenshot of it and trig it, or else you can trig it from the PDF attached. Then we are moving to D and F block elements. D block elements are the transition metals. They are having the incomplete D subshell in an atom of the common ionic form also. The electronic configuration follows N-1, D 1 to 10, Ns 1 to 2. But there are some exceptions like chromium, copper, palladium. Okay. And the physical properties of D block elements, that is, melting points are very, very high because the metals can easily form. They can tend to form a metallic bonding, which is stronger. That's why the melting points are high. Think about the iron rod. Okay. Then maximum at D5 configuration. And there are some exceptions like manganese, technetium are anonymously low. They are having low melting point. And zinc, cadmium, mercury are also low because D10 configuration is filled. Here I have D5 configuration, and in this case I have D10 configuration. Then talking about atomic radii, it decreases across the series as moving left to right in the period because of the poor shielding of d orbital. And the 3d to 4d radii increases as the number of shells increases, but 4d to 5d it is almost the same because of lanthanide contraction. Okay, and density is also generally increasing but the zinc density is lower because of completely filled orbital. Ionization enthalpy, it increases left to right, but not gradually, not steeply increasing. Because the electrons are partially shielded. Here we have manganese 2 plus, Fe3 plus are extra stable because of the half-filled configuration. It's really harder to ionize it further, so the ionization enthalpy will be very high. And chromium and copper, again, that will have very high second ionization energy, because after losing 4s1 electron, it will be completely filled or half-filled configuration will be there over here. Then talking about oxidation state, due to the incomplete d orbital filling, the middle row shows the most states. Like manganese is showing from variable oxidation state like +2 to +7. The maximum oxidation state, that it will be equal to the group number, and the heavier d block elements show the higher oxidation state. Zero oxidation state is exhibited by the metal carbonyls like a nickel carbonyl or iron carbonyls. Then the next important part is magnetic property. We know that paramagnetic, diamagnetic, and paired ones are paramagnetic and the paired ones are diamagnetic. And spin only magnetic moment formula. Always remember the number of unpaired electrons, that will be the starting number of your answer. Okay. Then colored ions, we already posted the shortcut to memorize the colors. Please do check out. And whatever given in your book, that list, questions will be asked from there only. Don't get distracted. Mostly the questions will be asked from there only. In the observed color, it's equal to the complementary color. Okay, whenever the electron jumps from the visible light and jumps to the higher d orbital, it's observing the visible light and jumps to the higher d orbital, what will happen? There will be an electron absorption. So obviously it will release that electron when coming back to the previous state. So this kind of electron transition will produce the colors. That's what DD transitions. Okay, and half filled and fully filled configuration. Mostly the fully filled configuration will be colorless. Then other properties like complex formation, catalytic activity, and interstitial compounds formation, there are the basic reasons, like these are the big ions, okay, and other ions like small, so that it can occupy the interstitial positions. Then catalytic activity means it is having lots of variable oxidation states, so that it can oxidize or reduce. Complex formation, smaller ionic size, what will happen? The high charge available to the d orbital, so it can accept the electrons from the ligand to form a complexes. Okay. Then here we have very important two compounds, that is potassium dichromate and potassium permanganate. The reactions involved here that can also be asked. First of all, in potassium dichromate, which is an orange solid, the chromium oxidation state is +6, and which can be prepared from the chromite ore. And the reaction of this is an pH dependent, right? So in acidic medium, how it changes, in basic medium, how it changes, that kind of questions can be asked. And in case of potassium permanganate, that is in +7 oxidation state, dark purple crystals. And here also see acidic, what is the electron oxidation number change, and neutral and strongly acidic, strongly alkaline medium, what is the change in oxidation state from the reactant to product, that is also important. And the structures, this is in tetrahedral and how the bond is formed. There I have a CR-O-CR bond, so that can also be asked. Then halides and oxides of d block elements. CuI2 does not exist because Cu2 plus oxidizes the I2 to I minus to I2. As oxidation number increases, what will happen? The ionic character decreases and acidic character which will get increases. Then F block elements. In F block elements, the main thing is lanthanide contraction. The steady decrease in atomic or ionic radius across the lanthanides due to the poor shielding of F electrons. So that is the reason for lanthanide contraction. What is the consequence? So consequence would be it will have similar atomic or ionic radii. That is the first point. 4D and 5D elements will have a same group nearly identical radii like zirconium and hafnium. And oxidation state, predominantly that is +3 oxidation state, but it can exhibit +4 also, +2 also. Okay, and the use is mish metal. So what is the composition is used? What are the other metals are used to prepare the mish metal? That can also be asked. Please do check out that. And where that is used, lanthanides are cracking catalyst, phosphorus in TV screens, phosphors in TV screens, and mixed oxides as a petroleum industry. Okay, that kind of questions can also be asked. Then actinides. Actinides, again it can show actinide contraction, and it shows the greater range of oxidation states. +3 is also common to all. The maximum oxidation state increases from thorium to neptunium and then decreases. Okay, and all actinides are radioactive in nature. So this is the key differences between lanthanides and actinides, and the important points is also given over here. Then chemical kinetics. In chemical kinetics, first of all, understand the reactant is decreasing, the product is formed. So the reactant is minus charge and the product will be plus charge. Okay, and what are the things affect the rate, concentration, temperature, catalyst, and nature of the reactant. Then rate law, order and molecularity. Rate law, you can just write rate is proportional to the concentration of the reactant, right? To remove the proportionality symbol, we will be using rate constant, that is A. The concentration which rises to the power of its coefficient. Okay, that is the rate law expression. Order of the reaction means it can be 0, starting from 0, 1, 2, 3 and so on. It can be even fraction also. But these are determined experimentally, not theoretically. In case of molecularity, the number of reacting species colliding in the elementary reaction, the simple reaction, that is molecularity. It is always a whole number. But it is not, we can't find it for the complex or multi-step reactions. Okay. So difference between order and molecularity can also be asked. Then there are first order reaction, second order reaction, third order reaction, zero order reaction. Mostly they will be asking questions from first order reaction and zero order reaction. So the zero order reaction is rate is A. Rate is independent of the concentration. Okay. And the integrated rate form can be written as R0 minus R by T half. T half means what? To complete the half of the reactant, how much time is required. Okay. So T half is equal to R0 by 2K. It depends on the initial concentration. And if you are plotting the graph between R, concentration of the reactant versus T, it will give you this straight line with the slope of minus. So which can be given like this, which will get this slope negative. Okay. Then first order reaction, it is dependent on the reactant concentration, right? It is dependent on the initial concentration. Half-life, that is independent of the initial concentration. Okay, half-life formula is T half is equal to 0.693 by K, and K is equal to 2.303 by T log R0 minus R0 divided by R. If you are plotting the graph between log R versus T, you will get in straight line with the slope of minus K by 2.303. Again a negative slope. Then there is an interesting topic, that is pseudo first order reaction. It behaves like a first order, but we technically speaking that is a second order, but it behaves like a first order. Okay. For example, hydrolysis of ethyl acetate, where we are using excess of water, right? But water and acetate I have this ester as a reactant, so this is second order we would think. But due to addition of excess of water, we are omitting the water content, water reactant concentration. We are just taking a ester concentration, which makes it as a pseudo first order reaction. Okay. Another example would be inversion of cane sugar. Hydrolysis of cane sugar to produce glucose and fructose. Then temperature dependence of rate. So for every 10-degree rise in temperature, the rate constant approximately doubles. Okay, so temperature coefficient, that's equal to K into temperature plus 10 divided by, what is the rate constant at plus 10 temperature? What is the rate constant at the T temperature? So that is approximately 2. Here comes the Arrhenius equation. Arrhenius equation, what it says, K is equal to A e to the power minus EA by RT, right? Each one of the term in Arrhenius equation is important. A stands for pre-exponential factor or frequency factor. EA is activation energy. R for gas constant, and T for temperature in Kelvin. So if I'm having two rates, Q rate constant, then log K2 by K1, that is EA by 2.303 by R into 1 by T1 minus 1 by T2. Okay, it is a very important formula. Catalyst it alters the rate of the reaction. So it provides the alternative pathway, so it lowers the activation energy so that more reactants can form a product. Okay, that is a positive impact of using a catalyst. There is another category of catalyst, that is poisonous catalyst, which can be used to reduce the speed of the reaction. Alcohols, phenols, and ether. Let's just quickly go through the theory part involved in this chapter. I'm just skipping those reactions. Let's see the classification: monohydric, dihydric, trihydric, and based on the carbon type, we have primary, secondary, and tertiary, and also we have allylic and benzylic, vinylic, depend on the hybridization present over there. There we have this monohydric phenol, dihydric phenol. Depend on that, the name will get changed. Okay, catricol, trisorcinol are also formed. Then ethers, symmetrical ethers and unsymmetrical ethers, where the two hands of the ether O oxygen is same, that is symmetrical. If that is different, that is unsymmetrical or mixed ethers. Talking about the nomenclature of alcohols, it ends with OL, right? In case of UPSC name, and in common name we use it alcohol itself, right? And phenols, the parent is phenol only. The substituents are present in 2 position, 4 position, 6 positions, or whatever the position from the OH group we will calculate it, right? OH is the first position, from there where the substituent is present over there, they will calculate it. And in the common name we mention it ortho, para and meta positions, right? Then structures of functional groups, alcohols, that is oxygen is sp3 hybridized, COH bond angle is less than 105 because of the lone pair repulsion, and CO bond angle is 142 picometer. Then phenols OH on sp2 hybridized carbon, and in ethers oxygen which is in sp3 hybridization happens over there. Okay, and phenol is more acidic than the alcohols because the phenoxide has ion that is more stable than the ethoxide ion or methoxide ion or alkoxide ion basically. Then physical properties, the boiling points of alcohols is more than the ethers or alkanes because the alcohols have the intermolecular hydrogen bonding in the ethers, and hydrocarbon doesn't have that. Okay, then the boiling point increases with the number of carbon atom increases because the van der Waals forces will get increased, and also decreases with the branching because the surface area decreases. Then solubility, lower alcohols, phenols and ethers are miscible in water because of the hydrogen bonding formation, and in case of higher the steric will be there, so it will not soluble. Solubility decreases eventually. Hydrophobic effect will be produced. Then preparation part, let's quickly go through these reactions and what is the rule it follows. First of all, acid catalyzed hydration, that follows the Markovnikov rule. Markovnikov rules means what? Rich getting richer, right? So OH goes to more substituted carbon, and first of all the mechanism, it follows like H3O plus that protonates the alkene, and then carbocation formation and attack of H2O that happening over there. Then hydroboration followed by oxidation, that is following anti-Markovnikov, and the addition is syn addition. These are the important points because we already know the reactions are everywhere. I'm just giving you this straight point. Okay. Then aldehydes, reduction of aldehydes or ketones to form an alcohol. Hydrogen palladium or sodium borohydride or lithium aluminum hydride you can use to reduce aldehydes or ketones. To produce aldehyde will give you primary alcohol and ketone will give you secondary alcohol. Reduction of carboxylic acid. Carboxylic acid, remember one thing, that will give you primary alcohols only upon reduction. Okay, commercially carboxylic acid which will give you ester to produce this alcohols. That is, catalytic hydrogenation happens. From Grignard reagent with carbonyl group which will produce alcohols. From methanol, I will get primary alcohol. Other aldehyde will give you secondary alcohol. Ketone will give you tertiary alcohol. Okay, this is a nucleophilic addition reaction of RMGX to carbonyl group. Then preparation of phenols from haloarenes. We are getting it from Dow's process. Okay, at very high temperature and pressure. And benzene sulfonic chloride using oleum, we are getting sulfonic acid. After that, we'll get into sodium phenoxide, then phenol will be formed. Then diazonium salt also, upon adding water, you will get phenol. And this preparation is very important from cumin. First of all, that will form cumin peroxide. And after that, the products are two. One is phenol, another one is acetone. These two products are equally important. Okay, the whole oil phenol production is using this. Because we are getting acetone also, phenol also. Both are equally important product. Then dehydration of alcohols to prepare ethers. At 413 Kelvin, dehydration happens. Okay, that is an SN2 mechanism. SN2 mechanism. Primary alcohol, we are using it to get ethers. At 443 Kelvin, you will get alkene. Okay. So 413 Kelvin, you will get ether. 443 Kelvin, you will get alkene. Okay. It's suitable for primary alcohols only for SN2 mechanism because SN2 favors that one. Secondary, at the tertiary, the elimination dominates. Then the substitution. Then Williamson ether synthesis. It is a laboratory method from alkyl halides with sodium ethoxide to produce ethers. We'll use primary alkyl halide for the best results. It is following SN2 substitution. Obviously, primary will be much more followed. What if I'm using tertiary and secondary? It will lead to elimination reaction. And chemical reactions of alcohols with active metals like sodium, it will eliminate the H2 gas. And acidity order of alcohols follows. Primary is more than the secondary, then comes tertiary. Because of the electron releasing group present over there, decreases the OH polarity. Okay, and alcohols are weaker acids than water, and alkoxide ions are stronger bases than the hydroxide ions. Esterification reaction that you know. And here comes the important one, the acetylation of salicylic acid, which will lead to the formation of aspirin. So salicylic acid, you know, right? Salicylic acid. If you do acetylation to it, which will lead to the formation of aspirin. Very important structure, please do take care. And with hydrogen halides, it forms the corresponding alkyl halides. And Lucas test. Lucas test will be using anhydrous zinc chloride with HCl. If that is in primary, if that is in tertiary, then that will show immediate turbidity. Then secondary will show turbidity at 10 to 15 minutes. And there is no reaction for primary. Okay, which clearly this is again a substitution reaction. So this is an SN1 substitution reaction. Then dehydration. The dehydrating reagent we are using as concentrated sulfuric acid and H3PO4. The dehydration happens in the order of tertiary, dehydrates fast, then comes secondary, then comes primary. Oxidation, the mild oxidizing agent, primary will give you aldehyde and eventually it will form carboxylic acid if you are using strong oxidizing agent. And secondary will form ketone and ketone kind of carboxylic acid like a lower number of carbons. Ketone to give carboxylic acid again. Then PCC is the best reagent for converting primary to aldehyde to get a good yield. And vapors dehydrogenation reaction happen means copper with 573 Kelvin we are using it for primary to aldehyde, secondary to ketone and tertiary to dehydration, which will form an alkene. Then chemical reaction of phenols. First acidity, that is much more acidic than the alcohols, right? So with bases it will form an phenoxide ion with water. Then effect of substituent on acidity, electron withdrawing group present over there, that will lead to ortho and para position. So nitrations, sulfonation, all those will lead to ortho and para positions only. So 2, 4, 6 trinitrophenol, that is a very strong acid which is called picric acid. It doesn't have any carboxylic acid group in it, but still that is called as an acid because that is having an, why picric acid is strong acid if they are asking question, you can easily answer nitro group, that is an electron withdrawing. So the OH hydrogen can easily leave from the OH, okay, which makes it very, very strong. Then electrophilic aromatic substitution, again ortho para directing group, it will lead to nitration, halogenation happens, and Coles electrolysis, phenol with NaOH to form sodium phenoxide, and then it will form 2-hydroxybenzoic acid, that is what salicylic acid is. That is ortho substituted product basically. Why is it so? Because it can easily form hydrogen bonding. Okay, then a very important reaction, that is Reimer-Diamond reaction, phenol with chloroform NaOH to form salicylic aldehyde, ortho position is formed. Then reaction with zinc dust, that can reduce the phenol to benzene. Then oxidation with sodium dichromate, which will form benzophenone. The structure will look like this. Sorry, it will be not a ring. Undergo resonance, but it is not a ring. It's a double bond. Then ethers. First of all, ether can undergo reaction with HX to form RX and ROH. Excess of HX, it will lead to more alkyl halides are formed. The electrophilic aromatic substitution for ethers that would follow, OR group is an electron withdrawing, so it will lead to ortho para directing positions. And it happens for halogenation, Friedel-Crafts alkylation, acylation and nitration. And important alcohols are methanol, ethanol, and the fermentation stops when an alcohol reaches more than 14% and the boiling point happens at 351. And the denaturation means adding copper sulfate with pyridine to make it unfit for drinking. So that is an industrial protection of ethanol. These are the important points for the board exams of this chapter. You can check out the PDF attached. Then haloalkanes and haloarenes, basic classifications and all we know, just quickly go through. And nomenclature, this is a basic thing. IUPAC rules, we are following the lowest Rocolant rule. And geminal dihalide, vicinal dihalide. Geminal means both the halogens are the same carbon. Vicinal means are on the adjacent carbon. That is the difference. Okay. And nature of CX bond. CX bond is a polar covalent bond because X is an electronegative atom. Right. So it will carry a negative charge and this will carry a positive charge. So what will happen? The electron cloud move towards halogens. Due to that, the bond length, which is shorter for the more electronegative atom, and enthalpy will be highest and reactivity will be least reactive. And chloro, bromo, if you compare, that will get decreases eventually. In the reactivity order, Ri will be more reactive than RBr, RCl and RF. Preparation of haloalkenes. First of all, we are using HX to produce a substitution reaction. You can use the Lucas reagent to produce halogens also, haloalkanes also. And using phosphorus halides like PCl5, PCl3, you can prepare it. And using this thionyl chloride, that is a very important method because in thionyl chloride we are getting, sometimes the question can be asked why this method is preferred a lot. Because SO2 and HCl byproducts are gaseous in nature, which can be easily evaporated. The yield of RCl or yield of this alkyl halide will be more. That's why we are preferring this method. Okay. Then from hydrocarbons, free radical halogenation happens and addition of HX to give alkenes. This is following an Markovnikov rule, and where it will follow anti-Markovnikov wherever the peroxide is present over there. Right? It's only for HBr combo, HBr with peroxide. There only anti-Markovnikov will be followed. Then addition of halogens to alkenes. This is in decoloration will happen. It is an important test of find the unsaturation. Then these two twin reaction. Filkinstein reaction for the preparation of iodides and Schwarz reaction for the preparation of alkyl fluorides. In Filkinstein, we are using sodium iodide with triether to produce iodide compound or alkyl iodide. And in Schwarz reaction, we are using a metal salts like a tin fluoride or antimony fluoride or silver fluoride. That kind of reagents are used. C Gopal fluoride can also be used to prepare the fluorides. Okay. Then preparation of haloarenes. Electrophilic substitution method, we can easily prepare the haloarenes. There comes the Sandmeyer reaction. We already saw from amines chapter, diazonium salts. Via that method also you can prepare Sandmeyer and Gattermann reactions. You can follow. Then physical properties of amines. The boiling points of haloalkanes are more than the corresponding hydrocarbons because of the dipole-dipole forces and van der Waals forces. And as usual, as the branching increases, the boiling point decreases. As the molecular weight increases, the boiling point will also get increases. Then density. Bromo, iodo and polychloro compounds have more density than the other ones. Solubility, these are slightly soluble in water, completely soluble in organic solvents. These are the chemical reactions of haloalkanes. KOH, of course KOH means what will happen? Substitution will happen. Alcoholic KOH only, elimination will happen. With KCNs, that's substitution. With KCN and AgCN, look at the difference. KCN, that is an ionic bond, right? It's K plus and Cl minus, which will lead to Cn, alkyl cyanide. In AgCl, I have this covalent bond that would be responsible for formation of the isocyanide. Okay, so these two are important. Sometimes they will twist you in the question. Then similarly, KNO2 and AgNO2, nitroalkane and alkyl nitrate, ONO and NO2, that is formed. NH3, that is forming amine, and NaOR ethers with RCOOAg, that is a metal with methyl carboxylase, which will lead to formation of ester again. As I told you, KCN and AgCN, that kind of question, nitrate kind of question can be asked, which is ionic, that is more important. Due to that, what will happen? The carbon will attract more or nitrogen will attract more. You have to decide. In this chapter only, SN1 and SN2 reactions are there. Please do check out our video. If you are unsure about SN1 and SN2, the overall the reactions of SN1 and SN2, I just summarized over here. In SN2 mechanism, there is a concerted step. It happens without any intermediate. Backside attack happens. The reactivity follows in the order of primary will be more, then the secondary, then comes tertiary. And in case of SN2, that is just opposite. Tertiary, then comes secondary and primary. It follows the two-step process. The intermediate is carbocation. So more stable carbocation would be the which will decide the reaction product. Okay. Then the comparison table I just have listed. Elimination reactions. Alcoholic KOH. Remember, alcoholic KOH will undergo elimination. I told you. So beta hydrogen and alpha halogens are getting eliminated. Okay. This halogen and this hydrogen will get eliminated to form the alkene as a product. Says the product would be the major product, which is a more substituted product. That is our major product. Then the reaction with metals. Grignard reagent, which will lead to the formation of, with metal, it will lead to the formation of Grignard reagent. And Woods reaction. Woods reaction, here we are using triether and sodium. That will doubles the carbon chain. If you give 2, I'll give you 4. So that type of reaction happens over here. It works best with primary alkyl halides. And why H2SO4 is not used with Ki? That is also another question asked. It oxidizes Ki to I2. We already saw this, right? Before it can react with alcohol, it just oxidizes. That's why we are preferring phosphoric acid. Then electrophilic substitutions, halogens are deactivating, but the substitution happens at ortho and para positions only, so it can undergo halogenation, nitration, sulfonation, Friedel-Crafts reactions and everything. Similar to Woods, we have Woods fitting and fitting reactions. Wood fitting means that's for combined of both. Fitting is for aromatic, Woods is for aliphatic. Woods fitting means aromatic plus aliphatic combined to give the addition product, substitution product. Okay. And polyhalogen compounds like chloroform, ferroin 12 can also be prepared. And what are the uses of these polyhalogen compounds? Those are also important. Please do check out. These are the important named reactions of this chapter. the important points. The next chapter, that is coordination compounds. This chapter basically involves three theories and isomerism part. Okay. First theory is Werner's theory. Werner's theory talks about only two things. First one is primary valency, which is ionizable ions. What are ionizable ions? Which is present outside the sphere, right? And secondary valency, that is referred to the coordination number. Okay, so for example, here we have metals show two positive linkages. These are the Werner's postulates, four postulates. Primary valencies are ionizable, satisfied by the negative ions, and the secondary valencies are non-ionizable and equal to the coordination number. Secondary ligands arranged in definite spatial geometry, octahedral, tetrahedral, and square planar. These are the four postulates if they are asking about the postulates. And here you see, sometimes they will give you the question like, these are the components are present in the given complex. So this dissociate to give and reacts with silver nitrate to form AgCl solution. So always remember one thing, whatever inside the sphere will not react with any other reagent. Okay, the molecules or ions outside the sphere only react. So through that, how many ions are precipitated, through that method you can find out what is the correct formula of the given coordination complex. Okay, and sometimes they will also ask the conductivity also. 1:3 electrolyte means 1 and 3. 1:2 electrolyte means this whole thing is 1 and 2 Cl minus. Like that you can do. And the next thing is, these are for basic terminologies like what is coordination entity, central metal atom, ligand, coordination number, coordination sphere, and what is counter ion. Counter ion, which is if the coordination sphere that is a negative, then the counter ion will be positive. If the coordination sphere is positive, then the counter ion will be negative. Okay, and oxidation number, while calculating the oxidation number, please make sure that whether you are dealing with the what type of ligand, bidentate ligand or tridentate ligand. Okay, and homoleptic and heteroleptic. Homoleptic means only one type of donor groups are there, for example this one, and heteroleptic, more than one donor groups are there. Here we have amine and chlorido, right? Then what are the types of ligands and denticity? Unidentate means only one negative charge, so only one pair of electrons are donated. Didentate means, or bidentate means two sets of electrons. Polydentate means more than 3. Particularly concentrate on this EDTA, EN, or other compounds like. Usually they will be asking these type of questions to confuse you. Okay, and EDTA, what is the full form of EDTA and what are the ions are donating over here? Right, it is in hexadentate, not not in tetradentate. It is a hexadentate. It is having 4 minus charge, but still that is an hexadentate. Okay, remember that. And ambidentate means 2 donor sites are there, but 1 at a time. Okay, please remember that. And chelation always increases the stability of the overall coordination complex because it is forming a ring or a cage kind of structure. For example, hemoglobin. In chelative effect, the complexes are more stable than the similar non-chelated complex due to the increase in entropy of formation. That is the reason. Okay, then we have IUPAC nomenclature. Here you have to remember few things. First, you need to concentrate on the positive part of the complex, whether it can be of outside the ring or outside the sphere or sphere itself. But you have to concentrate on the positive part first. Then entire coordination entity are enclosed with the square brackets and charged written in the square superscripts. Cations first, ligands named before metal. Negative ligands are ends with O sound, like chloride or chlorido, cyanido, oxalato, hydroxido, nitrito. Nitrito particularly, it is an ambidentate ligand, right? You have to mention whether oxygen is bonded with the metal or nitrogen is bonded with the metal. Okay. So N-nitrito for if nitrogen is bonded, O-nitrito if oxygen is bonded. The similar thing works for SCN also. Okay. Then you use mono, tri for naming, and oxidation state of the metal should be mentioned as in Roman numerals. If the ionic form is given, please mention that is an ion. Okay, in the end. And also if the complex itself is an anion, the sphere itself is an anion, you should end the metal name with an 8 sound. Like copaltate, chromate, cuprate, argentate, aurate, plumbate, like that. Okay. Then these are the examples of naming. I just mixed with other names also. See, What is this? NH2, CH2, CH2, NH2, which is nothing but ethylene diamine. Okay, EN. Sometimes they will give you EN, sometimes they will give you the full form. So please just be careful about that. Okay, and always remember when you are dealing with carbonyls, the oxidation state of the metal will always be 0. Okay, then isomerism part, geometrical isomerism, cis and trans, and fat and mer. Same formulas. Okay, cis means same ligands. Ligands are in the adjacent position. Trans means on opposite position. Right? It is possible in square planar A to B2 type. And in octahedral, X2L4 type, X3L3 type. So in X3L3 type only, we will get facial and meridional isomerism. It is not possible for tetrahedral complexes. And this important complex, cisplatin, which is used for the anti-cancer drug. Okay. Sometimes the questions can be asked in the way, tell me the difference between two geometrical isomerism and explain, and I'll give the example. Okay. So that time you can use this cisplatin example. Then optical isomerism. Optical means what? Non-superimposable to its mirror images. Right? Enantiomers, D form rotates the plane to the clockwise and L form rotates to the anti-clockwise. Right? It is common in octahedral complexes with didentate ligand. And this is an example of D and L form. Yeah, as I told you, A3B3 type of complexes exhibit facial and meridional isomerism. Just try to draw the isomer to make sure you know the answer perfectly. Okay. Then structural isomerism. Linkages means, as I told you, the ambidentate ligand speaks a lot here. Okay, NO2, SCN, CN, like that. And coordination ligand means interchange of the ligand within the coordination sphere. And ionization ligand means interchange of ligand and the counter ion happens. And solvate or hydrate, where the H2O molecules coordinator exchange happens with the outside the sphere, whatever the ions we have. Okay. Then the next theory would be valence bond theory. Valence bond theory is very simple. Here we have tetrahedral, square planar, and octahedral, and corresponding hybridization to it. Okay. In valence bond theory, they usually ask you about why this is paramagnetic, why this is diamagnetic. Particularly about this nickel complex. These two complexes, no? Nickel Cl4, nickel CN4. These two complexes, they have asked the questions a lot. Okay. Same type of questions they have asked a lot. And inner octahedral complexes means what is the hybridization. Outer octahedral complex means what is the hybridization. Why that is happening, they didn't mention it in PBT. That is a limitation. Cannot explain the color of the coordination complex. Does not quantitatively explain the magnetic data. And does not explain why some ligands are strong field and others are weak field. So these limitations are overcome by CFT. Right? CFT, basically, ligands are at the degenerate levels, metals are at the degenerate levels. Once the ligands are approaching the metal, it splits. Okay, it splits to, in case of octahedral, it goes like, let me draw it over here. If that is an octahedral complex, it splits like T2G and EG. EG goes an upper level and T2G goes to lower level. And the center part, which is called barycenter, and the upper level is gaining the energy, so must be represented in the positive, and the lower level is decrease in energy, so negative. So up to D3 configuration, there is no problem. 1, 2, 3, there is no problem. D4 configuration comes where the ligand have to go, whether it have to pair up with the T2G itself or it have to go to EG level. That is the confusion. That confusion is sorted out by the spectrochemical series. Spectrochemical series explains it is an arrangement of increasing the strength of the ligands. Okay, it's starting from the weak field ligand, ending with the strong field ligand. If there is a strong field ligand, it will undergo pair up. If there is a weak field ligand, it will go to the higher energy level. Okay, and for example, D4 configuration, here you see T2G and EG. The questions can be asked in the way, this type of questions. Del octahedral value, first of all, what is del octahedral? Here you see, I have this upper level and lower level to find out the CFSE value, right? And that CFSE value comes along with the del octahedral 0.6 and 0.4 values. So that del octahedral value is less than pairing energy. Then the weak field ligand, that is a high spin complex, And if that is more than pairing energy, then that will become low spin complex. Okay. Then we have colors of coordination compounds. In absence of ligands, d orbitals are degenerate. No dd transition happens. Ligands are the mainly reason gives the energy, motivate them to go to the excited level. So this splits to the d orbital, then electron absorbs the light and jumps to T2G and EG levels, so that the dd transition happens. So whatever the observed energy corresponding color, we will get a complementary color of that. Okay, which here the color chart, you know, right, how to remember that one. So just remember what is the complementary color of what. Okay, here I have listed some examples of the color observed and the complementary color. And bonding in metal carbonyls, remember one thing, in carbonyls I have an empty orbital. Obviously in metals also I have empty orbital. Ligands as a carbonyl, that will donate as usual to the metal empty orbital. But in case of carbonyl ligands, since that is also having empty orbital, metal is having an electron, it returns the gift. It's just giving us a return gift. Okay, so that makes the bonding stronger, right? So that will, the ligand carbonyl to the metal, that is the sigma bond, and metal to carbonyl, that is pi bond. Okay, that is pi bond. So it will, due to that, what will happen? The bonding becomes much more stronger. Okay, extra bond is there, no, it will create stronger. So that is what called as synergic bonding. Okay, then these are some examples to reinforce each other. The synergic effect are there that will strengthen and stabilizes the MCO bond overall. So also think about one thing. If let's imagine this one. Okay, this is giving another gift, no? So due to that, what will happen? There will be a bond length decreases. Bond length decreases between metal and carbonyl, and bond length increases carbonyl and oxygen, because carbon is moving towards the metal. Okay, so that type of questions can also be asked. Then these are the quick references for the structure and magnetic property. We already discussed in D block elements the Bohr magneton. Nu s is equal to square root of n into n plus 2, right? That is also given. And I told you, so many times I have told you, then unpaired electrons number, that is the starting number of the Bohr magneton value. Okay. And applications of coordination compounds. In analytical data, EDTA, DMG for the direction and estimation of the metal ions. DMG is particularly for nickel, and EDTA, it's forming a cage, 6-bar cage. Okay, it's not easy to escape. So that is for EDTA titration for water hardness, calcium and magnesium ions. In metallurgical purposes, we have this gold extraction, silver extraction and all. Okay, and biological systems, chlorophyll, hemoglobin. Sometimes they will ask you a question, what is the central metal atom in chlorophyll? What is the central metal atom in hemoglobin? Okay, and in B12, what is the central metal atom? That is Bhopal. Okay, so that type of questions we can expect. And medicinal purpose, I told you, right? Cisplatin. Cisplatin is used as an anti-cancer drug, inhibits the tumor DNA replication, but transplantin does not. And in industry, Wilkinson catalyst. If you studied the polymers chapter for advanced, you must be knowing this Wilkinson catalyst. Hydrogenation of alkanes, it is used, and electroplating with silver cyanide, gold cyanide. Okay, so those are the applications of coordination complexes. And sometimes they will ask you the difference between the double salt and the coordination compound. So double salt, which will ionize completely. Okay, if you dissolve this, if you tend to ionize this, it will produce iron, ammonium, sulfate. But if you ionize this one, it will give you potassium and this whole complex. Okay, that is the main difference between double salt and coordination complex. And these are the common mistakes you may do for mock test and the main test also. Please be careful about this. I'll be attaching the PDF. Please do check out. You can download. Let me know if you want us to discuss the important questions or sample papers of this board exam. Wishing you all the best.